Welcome to Ideal Vapor Compression Refrigeration Cycles, or VCRC. The purpose of this lesson objective is to discuss how engineers design air conditioning cycles that keep us cool during the sweltering summer heat. Many of us take for granted that the indoor climate control system allows us to live in comfort year-round. Whether it's a hot, humid, sunny afternoon or a frigid winter night, the temperature inside is maintained at a comfortable room temperature of 72 degrees Fahrenheit or 21 degrees Celsius. The technology used to do this is referred to as heating, ventilating, and air conditioning, or HVAC for short. Last lesson we learned that boilers superheat water into steam. That steam is then transported to radiators inside of buildings or rooms, heating the air inside the room. In smaller homes or businesses, a furnace is used where they heat the air in the high temperature reservoir, move it through the cycle by applying power to heat the temperature inside of the rooms. Two cycles that we discussed earlier for an HVAC system include a heat pump, where the high temperature reservoir is our desired outcome. Therefore, the coefficient of performance of a heat pump is the rate of heat transfer to the high reservoir divided by the power applied to the cycle. Using HIP to win, we know that the rate of heat transfer out of the cycle is negative, and our power into the cycle is also negative. A negative divided by a negative yields a positive value for our coefficient of performance for a heat pump. The maximum coefficient of performance for a heat pump is the temperature of the high reservoir divided by the difference of the temperature in the high reservoir with the temperature in the low reservoir. Again, all temperatures for coefficient of performance must be in absolute values. Today we'll be talking about refrigeration cycles, where the desired outcome is a decrease in temperature of the low reservoir, where our desired outcome is the rate of heat transfer from the low reservoir into the cycle divided by the power applied. The leading negative in this case ensures that our value for the coefficient of performance for a refrigerator is still positive. For the maximum coefficient of performance for a refrigerator, it is the temperature of the low reservoir divided by the temperature of the high reservoir with that of the low reservoir. If we look at an ideal vapor compression refrigeration cycle and expand our cycle here, we come up with 4 steady flow devices on the left. A vaporized refrigerant is forced through the compressor to state 2, which is at a higher temperature than state 1. That refrigerant then passes through the condenser, discharging heat into the high reservoir from the cycle. After the condenser, the condensed liquid refrigerant then goes through an expansion valve where a sudden decrease in pressure happens, turning the refrigerant into a mixture of vapor and liquid. Then the refrigerant passes through the evaporator where heat is added to the cycle, turning the refrigerant back into a vapor at state 1. Note that our heat transfer from state 4 to 1 from our low reservoir to the cycle is the room we're trying to cool off. This is figure 10.1 in your textbook. If we move further to the components, first we have the compressor, which pushes or forces a vapor refrigerant through the compressor when work is applied to state 2, increasing the pressure. The pressure at state 2 is greater than the pressure at state 1, and the temperature at state 2 is greater than temperature at state 1, providing us with a superheated vapor refrigerant. The refrigerant then passes through a condenser where a rate of heat transfer is conducted, turning the superheated vapor into a liquid refrigerant. At this state, P3 is equal to P1 because the condenser is isobaric and the temperature at state 3 is less than the temperature at state 2. Next, the condensed refrigerant will flow through the expansion valve where there's a sudden drop in pressure, turning the refrigerant into a mixture between condensed liquid and vapor, where the pressure at 4 is less than the pressure at 3 and the temperature at 4 is less than the temperature at 3. Next, the mixture of vapor and condensed liquid passes through the evaporator where heat is pulled in from the surrounding room returning the refrigerant to a vapor at state 1, where the cycle has completed and is ready to start again. If we look at the ideal VCRC with 4 ideal devices with no line losses, there are 4 processes. The first process is the compressor from state 1 to state 2 that is adiabatic and isentropic, therefore it is also reversible. The next process is where we go through the condenser, rejecting heat out of the cycle at constant pressure. The third process is from state 3 to 4, where a sudden drop in pressure occurs at the expansion valve, which is also adiabatic, shown here with our rate of heat transfer from 3 to 4 to be equal to 0. And the last process in the cycle is a reversible constant pressure evaporator, where heat transfers from the room into the evaporator, ultimately cooling the room in our low reservoir and heating up the refrigerant passing through the evaporator. Process 4 to 1 is also isobaric. If we break it down individually step by step, starting out at state 1, we know, or we assume, that our quality is equal to 1, placing state 1 on the saturated vapor line. We'll show this in red, moving from the evaporator to the compressor. Once power net, or power from 1 to 2s, is applied to the compressor, shown here as rotating shaft work, the isentropic compressor increases the pressure of the vapor to a superheated vapor at a new line of constant pressure at state 2s, shown here. Then the vapor passes through the condenser, where heat is removed from the cycle, changing the refrigerant into a condensed liquid at state 3, where the quality is 0 on the saturated liquid line. We'll show our line at state 3 is blue for saturated liquid. Once the refrigerant passes through the expansion valve, a sudden drop in pressure moves the refrigerant inside the saturated mixture region to state 4, shown here in orange. The final process is where the refrigerant passes through the isobaric evaporator, removing heat from the low reservoir into the cycle, returning our refrigerant to the saturated vapor line at state 1. This completes the cycle of an ideal VCRC. Next, if we look at conservation of momentum, the mass flow rate at 1 is equal to the mass flow rate at state 2s, is equal to the mass flow rate at 3, which is equal to the mass flow rate at 4. This is understandable because all of the processes inside of the cycle are one inlet, one exit steady flow devices. To analyze the ideal VCRC, we're going to use conservation of energy, or the first law for a closed system, where the change in kinetic energy equals the change in potential energy, which equals 0, and the mass flow rate is constant. We have isentropic relationships between state 1 and 2s, shown on our temperature entropy diagram. And as always, we have cycle energy balance, where the work per unit mass net is equal to the heat transfer per unit mass net. Applying the first law to our compressor, we have our heat transfer from 1 to 2s minus our work from 1 to 2s is equal to our change in enthalpy from state 2s to state 1. We know that our compressor is adiabatic, therefore the result is a negative work is applied to our compressor and is equal to the change in enthalpy from state 1 to state 2s. If we move to the second process, or the heat rejection through the condenser, we have the same first law, where the condenser produces and consumes no work. Therefore, our rate of heat transfer per unit mass is equal to our enthalpy at 3 minus our enthalpy at state 2s. The adiabatic expansion, or the third process, shows that we have an adiabatic valve as well as a valve that requires no work and produces no work. Therefore, the enthalpy at state 3 is equal to the enthalpy at state 4. We can see this further on our pressure enthalpy diagram, where the enthalpy at state 3 equals the enthalpy at state 4. And the last process is heat addition through the evaporator, where our rate of heat transfer from state 4 to 1 minus our work per unit mass from state 4 to 1 is equal to the enthalpy at 4 minus the enthalpy at 1. Being that the evaporator consumes no work and produces no work, we're left with the rate of heat transfer per unit mass from state 4 to 1 is equal to the enthalpy at 1 minus the enthalpy at 4. And if we have heat addition added to the cycle, our sign for this heat transfer is, that's correct, positive. Next, we'll look at our performance metrics for an ideal VCRC. Using the coefficient of performance from earlier in the lesson objective, we know that our coefficient of performance for a refrigerator is a negative value of the heat transfer from the low reservoir to the cycle divided by the power applied to the cycle. We can rewrite this as negative heat transfer from state 4 to 1 over the power from state 1 to 2s. The other performance metric we'll discuss today is the energy efficiency ratio, or a way to compare this cycle with other cycles. The energy efficiency ratio is given in units of BTU per hour divided by watts. That's how long it takes to cool a room off divided by the power put into the room. If we look at it, our coefficient of pressure is given in units of kilowatt divided by kilowatt, so it's a non-dimensional value. However, if we then convert one of the kilowatts into watts by dividing by 1,000, then multiplying by 3,413 BTUs per hour per kilowatt, we can start to cancel out some of the kilowatts, divide by 1,000, and we're left with our energy efficiency ratio in BTU hour per watt is equal to 3.1413 times our coefficient of performance for a refrigerator. We can also look at this as BTU per watt hour. This completes the lesson objective on ideal vapor compression refrigeration cycle.